Hello again, physics friends. We are back and talking today about the calculus of variations and its role in Lagrangian mechanics. What we're going to see is that the calculus of variations is a mathematical tool or set of mathematical tools that allows us to learn about a new formulation of mechanics. Instead of Newton's second law, we can use something called Lagrangian mechanics. Now, we've seen already what we've defined to be the Lagrangian. So we can write that out here. We've defined this as the difference between the kinetic energy and the potential energy. And we know that the Lagrangian depends on positions, velocities, sometimes time as well. It depends on the velocity mainly through the kinetic energy, 1/2 mv squared, and it depends on position through this potential energy, which is often a position-dependent quantity. What we learned is that if you write down the Lagrangian and you compute something called the action, which is the integral of the Lagrangian, then objects in nature take trajectories that give extremal values for that action. So we have this quantity called the action. Okay. Sometimes the symbol S is used for it, and this is the integral of the Lagrangian, which depends, as I mentioned before, on position, velocity, sometimes time. We're integrating that over time from t1 to t2. So this is a definite integral that gives a number, and that number is referred to as the action. And in Lagrangian mechanics, we're basically tasked with picking trajectories, x of t, and velocities, x dot of t, such that this action is extremal, meaning a minimum or a maximum or a saddle. And that's the basic idea. So mechanics, nature behaves in such a way that this quantity is extremal. So in mechanics, these particles are going to move on trajectories that extremize this action, and extremize in this context could be a minimum or a maximum or a saddle. We're not so concerned in whether it's a min or a max, but rather that the variation of this quantity, the action, is 0 to first order if you change the path around the correct path. So for the purposes of discussion, let's just assume that the action is minimized for the true path. What that means is if you took any other path, then this quantity, the action, would be larger than it is on the path that the particle actually takes. So this idea that particles move on the trajectories that extremize the action is sometimes called the principle of least action. And we use that term knowing that it doesn't necessarily mean least. It could be a min or a max or saddle, so maybe it should more properly be called the principle of extremal action, but principle of least action is what's most commonly used, with the understanding that it's not always the least. So I want to say a little bit about the Lagrangian and this idea of an action, and then where does calculus of variations fit in? Well, calculus of variations is a mathematical tool that tells us how to actually compute the quantities x and x dot, or positions and velocities, that extremize this action. So the calculus of variations is, given an integral of a function, how do we choose that function to extremize that integral? And that's a little bit different than calculus, meaning how do you find the min or max of a function? In that case, you're given a function and you're trying to find a value of, say, x that maximizes f of x. Here we need to choose a function that for which this integral is extremal. So we'll come back to that idea in a bit, but I want to say a bit about Lagrangian mechanics and this action principle, and then we'll come back and talk about calculus variations. This so-called action principle is very much a unifying idea in physics, so we're going to talk about it mainly in the context of mechanics, but the action principle is key in optics, in general relativity, in quantum mechanics. It's the tool that is used in research at the frontiers of theoretical physics. I mentioned it's used in optics, so you've kind of seen a consequence of the principle of least action before, right? You may remember Snell's Law. And in Snell's Law, we learn that the angle of incidence and refraction when a light ray crosses from one medium of index of refraction n1 into another one is related by n1 sine theta 1 equals n2 sine theta 2, right? So the ray gets bent at the interface between two dissimilar materials. Well, Snell's law is really just a consequence of a more general principle, which is the Fermat's principle of minimum time. And Fermat, who's shown here, and who lived in the 1600s, his principle of minimum time is that light takes the path that minimizes the travel time. So how does that apply in Snell's law? Well, imagine a ray of light, a photon, traveling from point A to point B. What is not the shortest distance, but what path takes the least amount of time? It turns out not to be a straight line path from A to B, but rather a path that is bent at that interface. So the claim then is that this path, the actual path that light takes less time than a straight line path. If that's true, then notice the straight line path would spend less, is a shorter distance in n2. So somehow light is willing to travel a longer distance in the top medium, and it still get to be faster. That must mean that the photon is traveling faster in the yellow medium than it is in the blue medium. So that tells us right away that n2 is going to be smaller than n1. And we see that borne out in the equation, right? If this angle theta 2 is larger, that must mean n2 is smaller than n1, so that this equation holds. But this equation is just one consequence of a much more general statement, that light takes the path that minimizes travel time. Lenses behave according to this, Snell's law, the fact that angle of incidence on a mirror equals angle of reflection, those are all statements of light taking the path that minimizes travel time. And that's a principle of least action. In that case, the integral, the quantity that's being minimized here is time, travel time, which you can write as the integral from of each little time step along the path. So you integrate dt all along the path. Now dt is a time, which is a distance divided by a speed, right? So the distance would be like a ds, where s is a little path length, like this, ds. And you divide that by the speed of the photon, but the speed of the photon is not always the speed of light. It's speed of light in vacuum, but if you're moving through an index of refraction or a material with an index of refraction that's different than that of air or vacuum, then the speed will be, in general, smaller. So you have to now carry out this integral to find which path the photon will take. Now, a reasonable objection, and one that was given at the time in the 1600s when Fermat proposed this idea, was how on earth could a photon know how long it's going to take on any given path before it takes the path, right? How does a photon choose a path that minimizes the travel time without actually having taken all possible paths to try them out? So that's where Richard Feynman enters in his formulation of quantum mechanics called the sum over histories. And the key idea that Feynman brought to the table was the photon doesn't take a path, in fact, that minimizes the travel time. The photon takes all possible paths, not just all possible straight line paths, but all possible paths from the start to the finish. So let's see what Feynman has to say about the action principle as it applies to quantum mechanics. So here we see Richard Feynman, and Richard Feynman is saying that in quantum mechanics, let's say you have a particle traveling from point A to point B. That particle actually takes not one path, but it takes all possible paths. And the probability amplitude that a particle will start at A and end at B is given by the sum of all of the amplitudes for all of the different paths. Now, each path contributes with an associated phase. And for the case of a photon going from A to B, you can think of the phase as being kind of an arrow in space, and that arrow is rotating, making one cycle at a rate given by the frequency of that photon. So like a blue photon will have its hand rotate more fast than a red photon because the frequency of blue light is larger than the frequency of red light. So in my mind, I'm picturing a photon traveling from A to B, and the photon is carrying with it like a hand on a clock, and that hand on the clock is spinning around and around as it travels. And when it gets to B, the hand freezes, and the direction that that hand points is like the probability amplitude for that photon. Then you can add up the ending arrows for the photon on every one of these different paths, and you add them up as vectors, and the overall arrow, the vector sum of each of the small arrows, tells you the overall amplitude for that process. So let's just see what that might look like for a photon traveling from start or source to a detector by bouncing off of a mirror. So here we have a source, S, and a photon detector, PMT, P, and we have a mirror down below. Now, light cannot travel directly from the source to the detector because there's a wall that blocks it, but light could bounce at point G and make it to P, which is what we know as the classical path, where the angle of incidence equals the angle of reflection. But Feynman's point is actually the photon takes all possible paths, even the ones that violate that angle of incidence equals angle of reflection path. And along each path, the travel time is different, right? Now you can see that the path S to A to P is going to take longer than the classical path that Fermat tells us about, the path of minimum time. Okay, so here Feynman is coming up with an explanation for the path of minimum time, but much more than that. So we can see that some paths will take longer than others, okay? And we see that there is a path of minimum time. So this idea is that as the photon travels on each one of these paths, you imagine a clock hand spinning around, and the rate that the clock is spinning around, that arrow is spinning around, is the same for all of these paths. Okay, so what that means is if a path is longer, the arrow will have spun more than if a path is shorter. Okay, so if you have think about an arrow associated with each of the paths, path to A, path to B, path to C, and so on, there's going to be an arrow associated with that path that points in general in a different direction. So we can look at what all of those arrows look like. And here is that plot, right? So the longer paths, like the paths that go via A and via M, those take more time, and the arrows for those paths point in the same direction as each other, and they point in different direction than for all of the other paths that point in different directions. Now notice path F and G and H all take approximately the same amount of time, and so the arrows, as indicated here, and so the arrows for F, G, and H are loosely aligned. They're not exactly parallel, but they're quite close. Whereas near the edges, the travel time changes quite rapidly. The function is steeper there, and so you have a larger change in the direction that the arrow points. So Feynman is saying, okay, take each of these arrows and just add them up as vectors, and you'll get the overall probability amplitude for going from source to detector. And that's what this plot shows. So you have arrow A added to B, to C, to D, to E, and so on. And after you have this kind of curly beginning and curly end, you draw a line from the start of A all the way to the end of M, and that's the probability amplitude for the photon to start at S and end at P. Okay, now you'll notice that most of that overall amplitude is provided by E, F, G, H, and I, and A, B, C, and D, they basically curl up and contribute very little to the overall amplitude, and the same with J, K, L, and M. So the paths near the edge don't offer much in terms of the overall probability, but the paths near the classical path are the ones that contribute the most. So this idea really is fascinating, and what we want to understand is how does Fermat's principle of minimum time relate to the sum over history's idea of Feynman, And also, how does Lagrangian mechanics relate to this idea as well? So that's where we're heading next. So I want to basically talk about, if this is what happens in quantum mechanics, how do we think about the so-called classical limit of this, in which only one of the infinite number of paths is selected? So to talk about this, I'm just going to refresh our memories a little bit. We're not going to get too quantitative, but I just want to refresh our memories a little bit about, in complex numbers, how you can represent a complex numbers as e to the I times an angle, and you can represent that complex number as an arrow in the complex plane, and the phi in the e to the I phi represents the angle of that arrow relative to the real axis. So if we think about each of these arrows of the photon as the phase of the photon, the direction of the arrow is representing the phase angle of the photon, and the phase is wrapping at a very high rate, dependent on the frequency of that photon as it travels. If you have large changes in the path, large changes in the travel time, you'll have large deviations in the orientations of those arrows. Whereas in regions where you have small deviations in the travel time, you'll have small deviations in the direction that the arrow points. In other words, the phase of the photon. Okay, so what is this? What plays the role of this phase angle in quantum? Well, it's e to the I times the action in units of h bar, s over h bar. So what we can see here is in the quantum regime, when the action is on the order of h bar, then in order to get the phase to wrap by 2 pi, you need s to change, you need s over s h bar to change by 2 pi. That means you need something on the order of 600% or 2 pi 100% change in s, the action, to change phi by 1 revolution. In other words, that photon arrow, you'd have to have a big change in the action in order for the arrow to spin 1 time. Okay. So this is kind of the quantum regime, right? When quantities in your problem are on the order of h bar, Planck's constant. But what about in the classical regime? In the classical limit, s will be much bigger than h bar. So I just pick a number. I mean, this is much smaller than the actual ratio. But what if s over h bar was 1,000,000, 10 to the 6? I mean, we're many orders of magnitude off of reality here. In the classical regime, this ratio would be 10 to the 30 or something. But let's just say it's 10 to the 6. If you want phi to change by 2 pi, right, then you need s to only change by a tiny bit, by 0.0001%. Okay, it's like 10 to the 6 over 2 pi. Oh, sorry, 2 pi over 10 to the 6. Okay, so if you think back to this travel time, in the quantum regime, right, these paths near the edge don't contribute much because the photon clock wraps many times there. Near the classical path, all of these points contribute similar amounts. In other words, their phase angle is comparable. But in the classical limit, you don't have to go very far away from G at all before the phase will wrap by 1 full revolution, essentially randomizing the phase angle. So what that means is in the classical limit, you're more and more of these paths, the ones that are not near the actual minimum travel time, they are all curled up and cancel each other out. And the only meaningful contribution to the total probability amplitude is the one that minimizes the travel time in this case. And that's where Fermat's principle of least action comes from. So in the classical limit, you select one path of many. And it's that one path that's the classical path. In the case of photon travel, it's the path that minimizes the travel time, because all other paths that deviate from that cancel each other out. And this does not just apply to the path that a ray of light takes. This applies to the path that particles take, right? In quantum, like, you can talk about any quantum particle, not just photons. It could be electrons, it could be quarks, and so on. So the idea then is that nature is fundamentally quantum, and that particles, photons or otherwise, explore all possible paths from point A to point B, and each of those paths contributes to the overall probability amplitude that the particle makes it from A to B. Classically, though, one of those paths is selected, and it's the one for which this quantity of the action is extremal. And that is what we get when we think about classical mechanics. Okay, so the idea then is that we're looking for the trajectory for which this action, S, is extremal, in this case minimal, so that small steps away from it do not change the action to first order. In regions where the action is not an extremal value, in this case a minimum, if we're away from the minimum, then all of the paths in that area are going to contribute in a way that creates a cancellation. So classically, only one of these paths is picked out. So we need to then, in order to do Lagrangian mechanics, we need to find a way to extremize this integral equation, to select the trajectory x and x dot that gives an extremal value for the action S. And the tool that we use for that is the so-called calculus of variations. So we're going to talk a little bit about the calculus of variations now that we have some motivation for why we need to do that. Okay, so how then do we find the trajectories that give extremal values for this quantity called the action, right? So we're going to think an analogy to calculus, okay? So in calculus, you might be given a function f of x, and maybe you want to find the values of x that give extremal values for the function f of x. And we know how to do that. We take derivatives of the function, or take a derivative of the function, and set it equal to 0. And that tells us the values of x that will extremize f of x. Could be a minimum, maximum, or a saddle. As shown here, min, max, or a saddle point. In each of those locations, the derivative is 0. The slope to the first order slope is 0. So just to make sure we're all on the same page here, let's look at a specific example. Okay, what if f of x is given by the function x minus 1 squared? So that's going to be a parabolic function. And instead of being centered on the origin, it'll be centered at x equals 1. So we have this parabola here that bottoms out at x equals 1 and y equals 0. So we know just visually and from experience that the value of x that extremizes this function is x equals 1, but let's just make sure we see all of the steps. The derivative of this function would be 2 times x minus 1. We set that to 0, and we say, x equals 1 is the value of x that extremizes the function f of x. So that's the process in calculus. Given a function, extremize it. But we are asking a different question here. We are saying, here is an integral. What functions x and x dot do we need to choose such that this integral is extremized? And the tool that we use for that is the calculus of variations. So it's a step more involved, more complex than extremizing a given function. And to be clear, this is a definite integral. And so the end result after you do this integration will be a number, like 12, okay? And it will have units. It'll have units of energy times time because you're integrating a quantity of energy and you're integrating it over time. So the question is, how do we choose x and x dot so that we maximize this number? And I think a really nice way of introducing the calculus of variations is to talk about how you prove that the shortest distance between 2 points in flat space is a straight line, right? I mean, we've all kind of stated that before and accepted it as obvious, and it probably is, but how actually do you prove this? Okay, so let's just talk through the proof. We're not gonna actually do the proof, but we're gonna set it up, and what we're gonna find is that the quantity that we're trying to extremize, in this case minimize, is the length of a total path, and we can express the length of a path as an integral of a quantity. So let's work through that. So here we're trying to start at A and end at B, and as I said before, we know that the shortest path is the straight line. I'll draw it in blue. But how do we know that? In other words, how do we prove that the purple path is longer? Okay, so that's what we're heading for today. So what we can do is we can think about chopping up each path or a path into little segments ds, and then we can write the total length of the path as the integral from a to b of all of these little steps ds. Okay. And we can go even further. We can put some coordinates down here, like so. And in a plane, we can call these coordinates x and y. And then we can think about this length ds, which I'll zoom in over here, call that ds. We can write that as a step in the x direction and a step in the y direction, so that we have ds would be the square root of dx squared plus dy squared by the Pythagorean theorem. Well, if we factor out a dx squared, we get a 1 plus dy dx inside squared. And when we factor out the dx from the square root, we get a 1 plus the x derivative of y squared. So the slope of the path squared shows up in that square root. So we could rewrite this integral over length as an integral of over x, and the quantity we're integrating is 1 plus the derivative of y with respect to x, which we'll call y prime squared. Add that to 1 and square root it. And this integral goes from the x-coordinate of point A to the x-coordinate of point B. Remember, it's an integral over the x-coordinate, and it's a definite integral. So here we can see that we have this quantity we'll call length. Well, the quantity is length, and our goal is to find the minimum length. So minimize length by choosing a path y of x such that when you integrate this quantity, which depends on that path, you get the minimum value. This structure is exactly the same as the action structure. Okay, here we're extremizing, minimizing length, and in mechanics we want to extremize the so-called action. In both cases, it's a definite integral of a function with respect to a variable. Here we're integrating a function with respect to x, definite integral. Here we're integrating a function of the trajectory and velocity of a particle, and the integral is over time. So we're not going to go through the actual derivation, or through the solution here. The calculus of variations is worked out in the reading, and in particular, this specific example is also worked out, and I strongly encourage you to read and work through that example carefully from the reading. But for now, we're going to stop here. The goal has been to talk about Lagrangian mechanics and specify how it's one case of a much more larger unifying picture in physics called the action principle. It applies to quantum. All of classical mechanics then you can think of as a limiting case of this sum over histories formulation of quantum mechanics that Richard Feynman introduced us to in the 1960s. And the solutions to those, or the determination of these paths, is found by extremizing this action, which requires a new mathematical tool called the calculus of variations that we're going to discuss and work through. And once you have that, then you're able to find all of the trajectories, or the trajectory that extremizes the action for a given physical situation. All right. So we're going to work through a lot of examples of calculus of variations and Lagrangians later as we progress through this course. But for now, we'll stop. And until next time, take care and be well.